Alright, hello everyone. I'm back for another video. This is a video on 1.B.1. We're going to be talking about the electron and the properties of the electron and the electron forces. So I have some pretty basic background information on the board behind me. It talks about the three types of subatomic particles, or rather the three subatomic particles that we're going to talk about in this class. There are many, many others, but that's more of a particle physics thing and not so much of a chemistry thing. So I'm going to step aside, please write these down, and then we'll talk about them. Okay, so I'm back. Hopefully you jotted down the notes. I'm going to fly through this pretty quickly because this is probably a review from even middle school. There are three types of subatomic particles: protons, neutrons, and electrons. Really the part that maybe you don't remember are the importance of the neutron. The neutrons act almost as a glue to hold the nucleus together. If you think about it, if you have all these protons in the nucleus, they're all positively charged, so they're all going to be repelling each other. So then you really should never be able to have anything above a hydrogen, because a hydrogen has one proton, but helium has two. And so the helium protons should just kind of fly apart. They should be repelling each other like a magnet. But somehow they're stable. And they're stable because of the neutrons. The neutrons kind of glue them together or hold them together through the strong nuclear forces inside the nucleus. And we're not going to really get into why they hold them together because that goes more into the particle physics realm, talking about gluons and quarks and all those other fun little subatomic particles. But just know that the purpose of the neutron is to kind of glue it together. That's why when you get to larger atoms, you can have isotopes of those atoms, but you never have thousands of isotopes, right? You only have so many combinations of protons and neutrons that are stable. You know, you can only have X percentage of your nucleus be proton before it starts flying apart. That's why things are radioactive. They don't have enough neutrons in their nucleus, and the nuclei just literally fall apart or rip apart because they don't have enough glue holding them together. Okay, out of these three subatomic particles, we're pretty much going to spend our entire year on electrons. Because electrons are responsible for nearly all the chemical reactions in chemistry. When we have two things react together, it's because atoms either share electrons, or they stop sharing electrons, or they take electrons from another one. That is pretty much what we see in reactions, the movement of electrons between atoms. Okay? Here's the thing. Excuse me. Electrons are attracted to protons. They're attracted to protons. Or rather, they're attracted to the positive charge of protons. Alright, so we have our negative electrons, and they're attracted to the positive protons. But they never actually fall right into the nucleus, right? If they were attracted, and they're orbiting the nucleus, if I have a nuclei here, and my electrons should just kind of theoretically fall straight in there. But they don't, because they have a velocity to them. Electrons are traveling fairly quickly, not nearly to the speed of light, but they are traveling. And since they have a velocity, that causes them to literally orbit the nucleus. Literally orbit the nucleus. And they orbit it in very specific shapes called orbitals. And it comes from the orbit, the term orbit. So they're attracted to the protons, but because they're moving, they never fall in. Okay, so electrons are constantly moving. They constantly have, I don't want to say the same velocity, but they constantly have at least a minimum threshold velocity. And they'll never go past that first energy level. Now, we can obviously add more energy to them by maybe heating them up or shooting them with different types of radiation. And they'll speed up. And when they speed up, they jump from a lower orbital up into a higher orbital. Okay, so electrons in the higher orbitals are just moving faster. That's why they're in a higher orbital. They're orbiting at a farther distance. For example, I don't know, planets, right? The outer planets may be moving faster than the inner planets, even though their orbit takes longer. It's just because they have a farther distance to travel. Okay, now that gets us to something called Coulomb's law. Now I'm going to erase all of this. And let's hope it erases well, because it's been up here for a little bit. Good. Right. We're going to talk about Coulomb's law and something called Coulombic attraction. Now, it's a fun term, It sounds super hard, but it's really not. It's fairly intuitive. It's fairly intuitive. We have something called Coulomb's law. It was made by a man, I'll assume Dr. Coulomb. He said that the attractive force, whoops, there we go, is proportional. Well, that looks like there. We got an A in there. That's proportional. That word's proportional. So you know, maybe A. Oh, there's an N. You'll figure it out. You can spell proportional. To the charge difference and inverse to distance. So let me once again step out of the way so you can kind of write this down. I'll come back and explain it. Okay, so Coulomb's law says that the amount of force, the attractive force between an electron and a nuclei, is proportional to the charge difference. So the greater the charge difference, the more force. Okay, so if I have an atom with a very large nucleus with maybe 90 or 100 protons, that's a big charge. That's a big charge difference. So it's going to attract those elements or those electrons very vigorously, very strongly. For example, like francium, or no, I'm sorry, not francium. But we'll get to that. We'll get to that example later. So the larger elements, or the larger the force, the more attraction there is. Think of the sun, right? This doesn't have to necessarily be about electricity or charge differences. We could relate this to gravity, right? This is very similar to Newton's law. The sun is very big, so the Earth is very attracted to it. The sun is large. However, it's inverse to distance, meaning the farther you go away, the less you feel that attractive force. Right? If we were standing on the surface of the sun, or right above the sun, we would feel a very strong pull towards the sun. Or if we were standing right next to a black hole, we would feel a very strong pull towards that black hole. However, since we're so far away, we really don't feel it. Right? People aren't flying off the surface of the Earth towards the sun. Even though the sun has larger gravity, larger gravitational force, we're far away from it. And since we're closer to the Earth, we feel that smaller force much more strongly. It's the same way with atoms. Okay? As those electrons move farther from the nucleus, they feel that attractive force less. They feel that attractive force less. So if I have a very big atom, like let's say francium is a very large atom. We'll go to the francium example. Francium is a very big atom. So it's going to hold on to its 1, 2, 3 energy level atoms or electrons very tightly. Francium's large. It has a lot of protons. It has a very large positive force. So the electrons close to it, it's going to hold on very tightly. At the same time, francium has 7 energy levels. And those energy levels, the distance grows exponentially. So if we have francium, let's say here's our nucleus. Our first energy level might be pretty close. Our second one might be farther away. Third one, fourth one. See how the distance grows? The distance between energy levels grows as you go farther out. So by the time you get to the 7th energy level, that electron's like way out here. Oops, sorry, I have toys everywhere, so I can't move. That electron's way out here. That's a really far ways from the francium nucleus. So that's the outermost electron. That's what we call valence electrons. That's a valence electron right there. And it's a really far distance from the nucleus of my francium. Therefore, even though francium has a very strong pull, this electron feels it very weakly. That's why this electron is very easily removed. This electron is very easily removed from francium because it has such a weak attractive force. It has a very weak Coulombic force, right, because of its distance. Now the good news is you never really have to calculate Coulombic forces. You just have to know why they exist and how they affect interactions between atoms. Atoms that have electrons very far out have very, very tenuous hold on those electrons. So the atoms in group 1 that only have one electron in that outer energy level, they have a very tenuous hold on that because of something called shielding. We'll talk about shielding in later videos. They have a very tenuous hold on that electron. And as a result, because they have a very tenuous hold because they're so far away. And as a result, it's very easy for those electrons to be taken by something else. And when they're taken by something else, you have a reaction. That's why they react with things like water. Water is very inert, doesn't really react with much. However, it has such a tenuous hold, water will take that electron from it. And that's why group 1 metals burst into flames in water, because of that electron transfer. So that's Coulombic forces. All right? So, it explains group 1 trends as well as noble gas trends. Okay? Noble gases are the exact opposite of our group 1. All right, noble gases, all the electrons in noble gases are held very tightly. They're very close to the nucleus. And so it's very hard to strip an electron off. It takes a lot of energy. We can do it, but just not very naturally. Okay? Sometimes you get things like xenon, the larger noble gases, it's a little bit easier. But still, the electrons are held so closely to that atom. That atom, the noble gases, are the smallest atom in their group because they have the most number of protons in that group. That period. So the row. So they're the smallest elements in that row because they have the most protons, and they're holding all of those electrons in tightly. And it's very hard for something to come by and strip an electron off. So they have a very high Coulombic force because their distance is so small. Francium has a very low Coulombic force because its distance is so large. Okay? It also explains something called ionization energy. Okay? Ionization energy I will abbreviate IE. Actually, I won't, because that is my abbreviation for example. Ionization energy is the energy required to strip an electron. So it's how much energy do I have to apply? How much energy do I have to apply to that atom to remove an electron? That's the ionization energy. How much energy does it take to turn an element into an ion? To strip an electron off of it. Okay, because I can apply an electrical current and it will strip electrons off of that atom. So how much energy? Okay? It turns out that there's a relationship. Okay? Weak ionization energy. Ionization. There we go. Energy. Weak ionization energy, meaning it doesn't take much to strip an electron, also means I have weak Coulombic, that's a B, oh boy, I just butchered that, Coulombic forces. Okay, so weak ionization energy means I have weak Coulombic forces. If it doesn't take a lot of energy to strip an electron, that's because it's not held very tightly. So they are linked together. Okay? And last but not least, we have one topic to cover. I know this video is getting pretty long. Actually, I don't know that because I don't have a clock in front of me, but I'll assume it is. Because all my videos get kind of long. So I get excited about the material and then I can't stop talking. Last thing we need to talk about is something called PES. That is photoelectric spectroscopy. Photoelectric spectroscopy. Ha ha ha. That's right, everyone's saying I can't spell. Got that one down. Photoelectric spectroscopy. PES. Okay? So, photoelectric spectroscopy, what we essentially do is we put an atom in a chamber and we pass energy through it. And we measure how much energy it takes to strip an electron. Now, and we keep doing that until all the electrons are stripped. And what that does is that tells us what element it is. Okay, so we have an unknown compound, or an unknown element, we put it in a chamber, we pass energy through it, and these electrons are going to start getting excited. They're going to be orbiting that nucleus, and they're going to get more and more energy, and they're going to spiral out until they eventually fling off. And we can measure it when they fling off. So a photoelectric spectroscopy is going to look kind of like this. And whoop, and whoop, and whoop. We'll do it like that. Okay? And these essentially are energy levels. So it would be like energy level 1, energy level 2, energy level 3. It's not exact, but it's pretty close. A small peak indicates 1 electron. A larger peak indicates 2. Okay? Now, since I made this up, this makes almost no sense. You really wouldn't see this scattering of peaks like it is. First off, you'd have 3 electrons in energy level 1. That's just ridiculous. Let me actually shorten that a little bit. Do a little smaller peak. There we go. But anyway, so what this is showing us, this is a way to show us where the electrons are. And it kind of proves this idea that the inner electrons are held more tightly because as we go up, the energy required goes up. Okay? So it takes very little energy to strip the first electron. It takes more energy to strip the second level, and even more energy to strip the first level. Okay, so as you go up, the energy level required, or the energy required to strip electrons from the energy levels increases. So it shows us that the inner electrons are held more tightly than the outer electrons. And then, of course, we can do this to identify. Since we have 1, 2, 3, 4, 5, 6 electrons in here, I know that that is also equal to the number of protons, which is also equal to the atomic number, and everyone, of course, knows that carbon is the 6th element. So this would be carbon. Okay? That's photoelectric spectroscopy. And we're going to cover that in class because that's a very important and somewhat tricky concept. You just have to look at a lot of PES data to kind of understand it. All right, hope that didn't go too long. Have a great day, good luck, and I will see you in class.